Examples of Fourier series. To find Fourier series of any periodic function, important steps are to find values of a0, an and bn, and to find values of these three coefficients. These are following important formulas in integration. First formula is integration e raised to ax sine of bx is given by e raised to ax upon a square plus b square in bracket a sine of bx minus b cos of bx. Second formula is integration e raised to ax into cos of bx dx equal to e raised to ax upon a square plus b square in bracket a cos of bx plus b sine of bx. And third formula is generalized integration by parts. If suppose u and v are two functions in integration, u is called first function and v is called second function, any independent variable can be used in integration. Then integration by parts is given by first function as it is into v1. Now this v1 means first integration of second function minus u suffix 1, and u suffix 1 means first derivative of first function into v2. v2 is twice integration of second function plus u2 is second derivative of first function into v3 means third integration of second function minus u3 into v4 and plus so on. That means go on differentiating first function and go on integrating second function, and alternate sign is taken negative. And this formula is very useful when first function is algebraic function. Then remember this integration by parts. Then we solve one example. First example, that find Fourier series of this function f of x is equal to x square in the interval 0 to 2 pi. Now it is always interesting or useful to draw graph of given function in given interval which represents one cycle of periodic function. Now f of x is equal to x square can be shown by this parabola. Vertical axis is f of x axis and horizontal axis is x axis. So this is parabola from 0 to 2 pi, and this graph represents one cycle of periodic function f of x. So same cycle after 2 pi, again same cycle after 4 pi up to infinity. So this is periodic function, and to find Fourier series of any periodic function, find a0, an and bn. a0 equal to 1 by pi integration from 0 to 2 pi over given interval f of x dx equal to 1 by pi integration 0 to 2 pi x square into dx, replacing value of f of x. Then integrate x square is x cube by 3 and limits are from 0 to 2 pi. Replace x by upper limit, cube of 2 pi becomes 8 pi cube, and 8 pi cube upon pi becomes 8 pi square upon 3. So this is value of a0. Then to find value of a suffix n. A suffix n is given by 1 by pi integration from 0 to 2 pi f of x into cos of nx. f of x is x square, and here we apply generalized integration by parts formula. X square is first function and cos of nx is second function. Then 1 by pi in bracket first function as it is, integrate second function. Integration of cos of nx is sine of nx upon n minus differentiate first function. Derivative of x square is 2x, and again integrate second function. Integration of sine of nx upon n is minus cos of nx upon n square, divide by coefficient of x, plus again differentiate first function is 2 and integrate again second function. Integration of minus cos of nx upon n square is minus sine of nx upon n cube, and this is last term of integration by parts because derivative of 2 will be 0 in next step. So this is end of integration by parts, and then limits are from 0 to 2 pi. Replace x by upper limit and replace x by lower limit. Usually values of sine are 0. So first check values of sine. Replace x by 2 pi, then becomes sine of 2n pi, and sine of 2n pi means even multiple of pi. Sine of even multiple of pi is always 0. So first term becomes 0 as well as last term also becomes 0 for x is equal to 2 pi. And if x replaced by 0, then again sine 0 is 0 and this sine 0 also 0. So first and last term becomes 0 for upper limit and lower limit. Then calculate second term carefully. Replace x by upper limit 2 pi. Now this negative and this negative becomes positive, and replacing x by 2 pi, 2 into 2 pi is 4 pi, cos of 2n pi, and cos of 2n pi is always plus 1. So becomes 4 pi upon n square. And replacing value of x in second term, x is 0, so becomes 0. So this is value of integration, and 1 by pi, 4 into 4 pi upon n square becomes 4 upon n square. So this is value of a suffix n. Now b suffix n obtained similarly by this formula, 1 by pi integration from 0 to 2 pi f of x into sine of nx, and replace value of f of x square into sine of nx dx. Again integrate by parts formula, 1 by pi, first function as it is, integrate second, integration of sine is minus cos of nx upon n, differentiate first function is 2x, and integrate again second function, integration of minus cos of nx upon n is minus sine of nx upon n square, plus again differentiate first function, derivative of 2x is 2, and integrate this function, integration of minus sine is plus cosine, so cos of nx upon n cube, and this is last term of integration by parts. Limits are from 0 to 2 pi. Now carefully apply limits. Second term becomes 0 for upper limit and lower limit. Then calculate first term. If x is 2 pi, becomes cos of 2n pi, and cos of 2n pi is plus 1, so gives minus 1 upon n, and replace x by 2 pi, so gives 4 pi square into minus 1 upon n is minus 4 pi square upon n. Then in last term, replace x by 2 pi, cos of 2n pi is plus 1, gives 2 upon n cube. So this value of last term for upper limit. Now replace x by lower limit and subtract. If x is replaced by 0 here, first term becomes 0 and last term becomes cos 0 equal to 1, 2 upon n cube, and subtract lower limit, so minus 2 upon n cube. 2 upon n cube gets cancelled, and cancel 1 pi is minus 4 pi upon n. Now after finding values of a0, an and bn, replace in Fourier series. F of x is given by a0 by 2 plus summation n from 1 to infinity a suffix n cos of nx plus summation n from 1 to infinity b suffix n sin of nx, and replace values of a0, an and bn. a0 by 2 becomes 8 pi square upon 3 upon 2 is 4 pi square by 3. Replace value of an 4 upon n square, and replace value of bn. So this is Fourier series of given function in given interval from 0 to 2 pi.